Hi everyone, thanks for checking out this video. So if you guys have been watching this series so far, in the past couple of videos, we first downloaded this melanoma image dataset. Then we processed the data using this program here to get these training and testing NumPy arrays with all the images and their labels, get them into these this like nice format to use for the training and testing. Then we made a PyTorch convolutional neural net that we defined as a class in this program here. Called it just the net class. This is our convolutional neural network that we made using PyTorch. Then we trained the data using this training image dataset. Showed you guys how to write all the code to do the training. Again, using PyTorch. And now we're at the point where we have our trained model saved here, saved model.pth, and it's time to test the model on our testing data set to see how accurate it is. So if you guys don't already know, kind of like the basic idea of machine learning is that you want to use some training data to fit the parameters of your model to get your model to like detect patterns in the training data. And then after you've done that, after you've done the training, you then want to give it some different data called the testing data set to then see if it can correctly generalize the patterns it found in the training data, if those patterns generalize onto new data that it hasn't seen before. So the point of the testing data set is these are some images where we know what the answer is, but the model hasn't seen these images yet. So basically we're going to see if it found any pattern in the training data that it can now use to correctly classify these testing images that it hasn't seen before. Okay, so we're just going to import the usual stuff up here, NumPy, Torch, and then import our net class from this file here. And then what we need to do first is we previously saved the model. It's here. It's called saved model.pth. So we need to read this back in. So first, we're just going to make a net object using our net class. Remember, this is the one we defined over here. We're just going to make an empty net object, and then what we're going to say is net.load state dict parentheses torch.load and then quotes saved model.pth. So basically this is taking our trained model that we saved here and it's just loading it back into this program so that we can keep using it. And then we're going to say net.eval. So basically this line here, net.eval, is putting the trained network in evaluation mode. So basically letting PyTorch know that right now we're not doing any more training. We're now at the point where we're going to be evaluating the model. And that'll cause PyTorch to do things a little bit differently on the back end in terms of how it's doing some things. Okay, so now the other thing we need to do is we need to define our image size. So it's like we've been doing. I've been telling you guys so far. I just put this at like the top of all of these programs just so that we can access it whenever we need to. Actually, maybe I should have done that first. That even should be up here. Just so we can easily find it in all of the programs. So yeah, define the image size 50 pixels by 50 pixels. Yeah, okay. So then what we need to do next is we need to read in our testing data. So the syntax for this is going to be pretty similar to how we read in the training data. I'm just going to read in this NumPy object that we saved. So it's going to be testing data, And remember, it's like we saw before in the training data. It's basically the same format. You know what? I'll show you guys again just to take a look at it. Basically, every element in this NumPy array has two sub-elements, and the first sub-element is the array representation of the image. It's a 50 by 50 two-dimensional array representing each pixel of the image. And then the second sub-element is the one-hot vector label that tells us whether it was a melanoma image or a benign image. But yeah, I'll just print this out just to show you guys what it looks like. Oh, whoops. Sorry, guys. Should be testing data here. Sorry about that. Yeah, so this is like the first element in this NumPy array. So this thing here is the actual like array representation of the image. And then this is the one hot vector telling us if it's benign or melanoma. And we can see this is a benign image because it's 1, 0. Let's see if we can find a melanoma one. Yeah, so this one's melanoma. It's because it's 0, 1 for this one hot vector. And then, yeah, these are the actual like image arrays. Okay, so it's like I said, like each element in this NumPy array has 2 sub-elements. So what we need to do next is the same thing we did in the training video. We need to unpack these things and get them into separate tensor objects. So yeah, I'm just going to copy and paste from the previous video, change all these to be test, and then I'll explain what they're doing in a second. Testing, okay. Okay. Yeah, so basically this is just unpacking, it's like unpacking, this part here is unpacking the first sub-element for every element in this testing data NumPy array. So we're basically just taking all of these like image arrays and then putting them into a list, and then at the end we're casting this list of all these image arrays into a torch tensor object. And then after that, we then need to get all the numbers, instead of being between 0 and 255, we want to get them between 0 and 1. So we're just normalizing them all by dividing by 255 there. And then I'll show you guys what it looks like after that if we just iterate through this the items in this test X tensor. Yeah, so these are all of our image arrays here. Okay. Oh, and by the way, this is kind of convention to call the input data as capital X and then the labels as lowercase y. You guys can call these things whatever you want, but yeah, this is a bit of a convention for both the training and testing to just, yeah, calling the input data X, and then, yeah, the labels are lowercase y. It's a bit of a convention. And yeah, this is kind of doing the similar thing. This is unpacking these one-hot vectors that we have down here. We're trying to unpack these and put them also into a torch tensor object, so that we'll have, rather than everything being packaged together in the same NumPy array, we'll have 2 tensor objects where the first one is all of the image arrays, and then the second one is the corresponding one-hot vector labels that tell us whether all the images are benign or melanomas. Okay. Yep, looks good so far. So now what we're going to do is we're going to go through all of these images and run them through the model and get the model prediction about whether they're melanoma or benign. And then we're going to check the label and we're going to see if they're actually melanoma or actually benign. And then we're going to see if the model got it right or not. And then we're just going to like keep track of how many gets right and how accurate it is overall. So I'm going to say correct equals 0. Total equals 0. Then I'm going to say with torch.noGrad. So this is like a bit of like a technical thing here, but basically this is saying that so when you're doing like the training and stuff, PyTorch keeps track of the gradients for things like automatically, and it'll keep track of the gradients unless you specifically tell it not to. So we don't technically need to write this. Like we could do all the testing with it still calculating all the gradients, because just because it's calculating the gradients, like it's not doing anything with the gradients unless we tell it to. So we could still do the evaluation and just allow it to calculate these gradients and just not do anything with them, that could still be okay and that would be fine. But that would be wasting compute basically, and it would just be an inefficient thing that we'd be doing that we don't have to do. So I'm going to say with torch.nograd, so that we can specifically tell PyTorch, like, okay, for this part, you don't need to automatically keep track of the gradients. So I'll make a note of that. Tells PyTorch not to automatically keep track of gradients. So yeah, that'll just make the whole thing a little bit faster and more efficient. Again, even if we didn't write this, we could still do the evaluation because it's not doing anything with those gradients. It's not optimizing unless we like specifically call the optimizer. But yeah, keeping track of the gradients takes computing power, and we don't want it to have to do that if it's not using the gradients anyway. But okay, so yeah, moving on. So I'm going to say for I in range len test x, basically iterating through all of these image arrays we have, and then so for each one, the first thing we want to do is basically just like pass this image through the model and get the model prediction of whether it's benign or melanoma. So before we actually pass it through, I need to cast it to be like, I need to like reshape it to be like the right size to pass in. So I'm going to say test x index I. This is our image that we're working with. We're not batching here. We're just doing it one by one for these images. So I'm going to say view -1. Again, -1. Not even sure if it's necessary, but why not use it? I don't want to break anything. You know what I mean? So the -1 here is basically just saying to PyTorch to like give it some flexibility in terms of the dimension here. But yeah, -1, and then the dimension that we're actually passing through is 1 image size. So technically, the original images after our processing were like 50 by 50 pixels, but PyTorch has this quirk that I've been talking about where whatever the dimensions are, it has to be 1 by those dimensions. So instead of 50 by 50, it's 1 by 50 by 50, basically. So yeah, that's just how it is. Yeah, and then so now it's ready to be passed through the net. So I'm just going to say net, and then just basically pass this whole thing through our neural net object that we have. Yeah, passing it through. And then, so let's just print out what this gives us. So I'll just say like output. Let's just print out what this gives us to just take a look at it. I just like taking a look at these things just to see what we're working with here. So let's just see what we get here. Okay. Yeah, so it gives us this tensor where it's like this one here is the prediction, like the predicted probability that it's benign. And then this one here is the predicted probability that it's melanoma. So I'll just copy and paste in again the same kind of hint that I put in the training thing here. It's like this is like the real label. This is just a good reminder. This is like an example of what one of the real labels might look like. It's this one hot vector, and this one tells us that it's melanoma. And if it was benign, it would be 1, 0. And then this is the guess. So the guess this guess is basically saying the model thinks there's a 66% chance that it's melanoma and a 34% chance that it's benign. So we would say that this would be a guess that it's melanoma with 66% confidence. So yeah, this is an example, and then this is like the real thing. So this is basically saying like about 81% chance that it's benign according to the model, and about 18% chance that it's melanoma. So we would call this a benign guess. Okay, but we need to unpack this a bit because we can see this is like a list of a list in here. So we need to get just like the first element of this thing, and then from here we're going to say if output, remember, yeah, this is just taking this inner list. It's basically the 0th element of this other list, the 0th and only element. So yeah, we're just going to put index 0 here. Don't forget about that. and then we're going to say if the first element, if this first number, if the first number is greater than the second number, we're going to say guess equals, I'll just say B for benign. We don't have to, because I was thinking, should I write the whole thing? But I was thinking, no, I always spell it wrong. I always spell it like that when I'm typing it quick. So I'll say, no, I'm not even going to try to spell it. I'll just say B for benign. And I'll say else guess equals M for melanoma. You guys might notice there's like a tie here, but since this is a binary classifier, it's not going to know what to do with the tie. So I'll just say if there's a tie where they're both exactly 50-50, then we're just going to guess melanoma just as a tiebreaker. Actually, you know what? That doesn't make any sense. It should be the other way around. It could be either, but you know what? There's more benign moles in real life than melanoma moles. So I'll say the tie goes to the benign guess, even though the training and testing are like 50-50 each. Yeah, I'll say if it's a tie and they're exactly 50-50, guess benign, otherwise guess melanoma. So that's our guess. And then we need to check the real label. So I'm just gonna again like print out what the real label is here. I'm gonna print test lowercase yi. This is going to be our real label telling us what it actually is. So I'll just print out this and see what it looks like. And yeah, so we can see the first real label. It's a benign one. So the model actually apparently got that one right. So yeah, this is what it looks like. And we're basically going to do the same thing here, where we're going to say if you know what? I'll just to make it more readable, I'll just assign here. I'll say real label equals test y index I. Say if, and then yeah, then we can just copy and paste this whole thing, and then just say real label. If the first number is greater than the second number, it's never going to be equal because these are all one-hot vectors. But I'll just keep the syntax the same anyway. If the first number is greater than the second number, like in this case, then the real, let's say real class equals benign, and then else real class equals M for melanoma. Okay, so I hope you guys are all following this part. This is just checking what the model prediction is, whether the model's predicting benign or melanoma, and then checking these one-hot vectors to see like what the real label is, whether it's benign or melanoma. And then from here, we just want to check if we got it right or not, or I mean, if the model like made the correct prediction. So we're going to say if guess equals real class. If we're guessing the same thing that's the same as the real class, either benign or melanoma, then we're going to say correct plus equals 1. That's another way of just saying correct equals correct plus 1. And then total plus equals 1 no matter what. Okay, and then last thing we need here, this will go through the whole testing data set. And remember, the important thing here is that the model hasn't seen these images before. The model's been trained on the training data. The testing data, it hasn't seen these images before. So we're seeing if it can get these right, even though it's been trained on these other images, if it can correctly like generalize some kind of pattern it found to be able to make correct predictions about these images it hasn't seen before. So then the last line we're going to have down here is, I'm just going to be a bit lazy, copy and paste to print out the accuracy. So I'm going to say print f string accuracy, rounding the fraction correct divided by the total, round that to 3 decimal points. So yeah, this is just the fraction that it got correct out of all the total number of images we gave it from the testing data set. Okay, yeah, hopefully this will work okay. Yeah, let's give it a try. Hopefully it'll work okay. Okay, so this is the accuracy. It was accuracy of 0.838. This is okay accuracy. It's kind of like I said. It's kind of like I said in the intro video for this series. the point of this series is to like get you guys started. If we were actually trying to do like real research, like to make an application to like use at a hospital, then this would be, of course, nowhere near good enough. You can't be only getting it right 83% of the time if you're actually a doctor like diagnosing these things. That would be like really bad for a doctor. But hey, like for something that took us only maybe like an hour or two to write this whole thing, yeah, we wrote this with no medical training at all. We wrote this program in like an hour or two, and it's getting 83% accuracy on these melanoma images. Yeah, like all things considered, I think that's pretty good. I mean, if it was just randomly guessing, it would be getting like 50% correct just due to chance. So yeah, like 83 is not bad. But yeah, it's like I said, this whole series has been kind of like a starting off point for you guys. This is showing you guys like how to do the basics, how to write a neural network, like the basics in PyTorch, and then how to like process the data, how to make the training and testing data sets, and how to do like the very basics. Yeah, if you guys are doing like real research, you're gonna have to kind of continue on from this point to try to get to like maybe 98% accuracy or something to have it be actually useful. But yeah, some ways to do that, possibly making a more complex network, possibly throwing more compute at it, possibly having more epochs, more training data, possibly doing like kind of permutations of some of the training images. Yeah, there's a bunch more advanced strategies that if you guys want to do more of this research, there's a lot more to learn from here to get to the point of like really being able to make like a highly accurate model. But yeah, like all things considered, for a first step in a couple hours, yeah, like 83% accuracy, I think that's pretty good for just kind of starting out. And yeah, so this is kind of like at least a decent starting off point for you guys. I think I'm going to make one more video after this. I think I'm going to make one more video to show you guys how to take this network and kind of package it in to a somewhat user-friendly function in Python. So yeah, that'll be like an optional like final video, just trying to make this whole thing like a user-friendly function like I showed you guys in the intro video. But yeah, if that's like optional, so if you decide to stop here, that's okay too. But yeah, thanks for watching, guys. The code will all be up on my GitHub if you guys want to download it. Any questions, just let me know in the comments and I'll try to answer them. But yeah, thanks for watching, guys, and see you next time.